also wonder what will the system will do when they see the statements like select from where. Actually, once the system have a core input like the select from where, what we do actually is to begin with a relation in a from clause. This from clause indicating the table we're working on, right? So we begin with a relation in the from clause, and then we can apply the selection indicated by the where clause. I mean the conditions we have. So based on the condition we have, we can go over all the rows, check one by one to see if the condition can hold or not. And then we can apply the extended projection indicated by the select clause and to return the desired attributes true as a result for the query. So the semantics for select from where statements will be like to implement the algorithm thinking of this type of reliable ranging over all the tuples of the relation mentioned in the where clause, and we can check if the current tuple satisfies the where clause or not, and if so, then we can compute the attributes or expressions of the select clause using the components of the tuples. You can implement these statements by the C++ or Java as well. However, it will be fine. It will be very complicated if we write the same thing with the C++ or Java. We need to handle all the details very carefully. However, with SQL, we can do this kind of queries very easily. Just write down select from where, right? And select from where, the example we showed before is just one example. Actually, sometimes we don't need to select some attributes. We just want to return all attributes. If so, then you can use a star in the select clause. What does this mean? When there is a one relation in the from clause, the star in the select clause stands for all the attributes of that relation. Right? So we can have an example by using the beers we used before. Right? We can select star from beers where manufacturer equals to Bush, and the return result will be like this. It will be a table, right? And this table will have two attributes because we select star here. Star means all the attributes, right? In other words, from beers we project all the attributes in the beers table, then manufacturer in the return result. We have then manufacturer here, right? And we have a condition is manufacturer equals to Bush, and you can find in the return result for this table the manufacturer always equals to Bush. Right? So we can even start in this way by project all the attributes. I think you can either write down the query in the select from where statements using the relational algebra as well. And again, you can compare them with each other. You will find this style can be very helpful and very useful as well. Before in the relational algebra we mentioned, we can have a function. It is called renaming, right? Renaming both the relation and attributes. And we will implement that in the SQL as well. So we can rename some attributes. The way we do rename is like this. If we can do the result have a different attribute names, then we can use this as followed by a new name for the attributes to rename an attribute. And I'll show you an example of this renaming as follows. We are still working on the beers is table with name and manufacturer. We plan to change name to beers instead. In other words, we can write this SQL query we showed before as select name as beer. It means we change the name to beer instead in the return result, and comma manufacturer. In other words, we select two attributes in the statements, both the name or the beer and the manufacturer. From beers, where the manufacturer equals to Bush. So by executing this query like this, we will have a result showing at the bottom. We will have a table, right? First of all, the return result is a table. In the table, we have two attributes. The first one is beer, because we change the name to beer in this statement, right? The second one value is a manufacturer. And for all the tuples in the table, the manufacturer equals to Bush because it is a condition, right? So we can do the renaming of these attributes very easily in the select from where statements. Besides renaming, we can also do some interesting things in the select clause as well. For example, we can use the expression in the select clause. What does this mean? Actually, any expression that makes sense can appear as an element in the select clause. Here we use the example of the sales table with bar being a price. It means the bar should be with some price. And we plan to write a query to find the bar being a price. And here we change the price from USD to the Japanese yen instead. We can do so by writing a select from where clause analysis, select bar beer price times 120 as price in yen from sales. Here we finish, we don't have a where clause. So by executing query like this, we're working the sales table and we return the same table. The main difference in the return result compared with the sales table is we change the last attribute from price to price in yen. This price we used before is the USD and the US dollars, and price in yen is Japanese yen. And we'll make some changes to price values. We times this price with 120, which is the exchange rate between USD and the Japanese yen. So in the return result, the table is almost the same as the sales table. However, we change the last column, we change both the attribute name and the word values of the data tuples. Here another difference is we don't have a where clause. In other words, we don't have any condition for selections. We will return all the data tuples in the table. And what we can follow me for this example. I hope you still remember in the original algebra we showed before, we mentioned that in the selection, this condition we use can be very complex, right? It will be very similar for the SQL as well. We are now very complex conditions in the where clause. What does this mean? And let's assume we are working on this sales, this table, and we plan to find the price that Joe's bar charges for the cheap beers. So what do we mean by the cheap beers? We say a beer is cheap if the selling price is less than $5, and we plan to find the price of these beers. Before we check the SQL query, you can write down this query with relational algebra first, and then you can translate to SQL. So we can write down this query in SQL like this. We select price because we want to find the price, right? And we are working on this sales table from sales. And the condition in the where clause will be like the bar equals to Joe's bar, right? Because we want to check the price in the Joe's bar, right? So we need to have a condition, the bar equals to Joe's bar, and the price is less than $5 because we want to check the price of these cheap beers, right? So the price is less than $5, denoting this beer is a cheap beer. In this way, we were able to return the price for its cheap beers sold by the Joe's bar. Right, I hope you can follow me. So we are now very complex conditions in the where clause. This one we combine two conditions via this and. And besides this and, we can also use some other operators to help us define some complex conditions. Generally, when we write down for this where clause, for the selections, and we can use all the attributes or the name of the attributes appearing in the relations used in the from clause. And we can use many different comparison operators like equals, not equals, less than, greater than. We can also use some like operation to change the values by times some values like times 2 as well. And we also know some like operation on strings like the concatenation of the strings, as well as some orders on the strings. And we also know this we do the matching between some string versus some patterns. We can check if a string is like some pattern or not as a condition. And we also know some special stuff for comparing the dates as well as time as well in the where clause. So you can define this condition in a where clause depending on your problem or your application. And we are now very complex conditions. We also have some reminder for you because we have some details in SQL. So first of all, SQL is case insensitive. Generally, the query we write down, you can either write down them in like an uppercase or in the lower case. It doesn't matter. However, we have one exception. If we have a string which is quartered, and then it will be case sensitive. For the other cases, they will all be case insensitive. And if we plan to use a single quarter inside a string, then we may have to use two single quarters in the string to represent the single quarter. Let's assume if we have a string like this, right? And here we have to use this single quarter. If we plan to use a single quarter in a string in SQL, then we have to use two single quarters here to represent this one is a single quarter inside a string. Right, you can follow me, right? And in the condition in the where clause can use this and or not in the parentheses in the usual way, like the Boolean conditions, which are built. So when you write down the query in the relational algebra, you can translate the condition you write down into SQL very easily, because we are now all very complex these conditions as shown as we use in the relational algebra. Here we can show you with some more examples about this where clause. So in the where clause, we can compare the string with a pattern to see if it can match or not. So the general way to do this matching of the strings will be like, so we have the attribute name like some pattern. This attribute name denotes a string in a relation, right? Or we can use this attribute not like some pattern. So what do we mean by a pattern? Pattern is also called a string. However, in this quarter string, we have some special characters. The first one is 100%, this marker. We use this 100% denotes any string. And at the same time, we also use this underline denotes any charge. So for example, given the drinkers table, we have name, address, and phone number. We plan to find the drinkers with this exchange number 555. We can do so by select the name of the drinker, right, from the drinkers table, where the phone number is like 100% 555 and followed by some other phone numbers. So here this 100% denotes some strings before 555, right? And these underlines, we have four underlines denoting any four numbers. In this way, we can match this phone number with this pattern, with any numbers before 555, and we have 555 in the middle, and also followed by four other numbers. This defines the pattern for the phone numbers, right? With 555 as the exchange number. So this is for the where clause. Besides this, we also need to pay attention to the where clause as well, because before we assume in the where clause for all the attributes we are matching, we are comparing, they have some values. However, in the real world database systems, we know this null value, if you still remember, right? We know some attributes to have null value. And if we plan to match or to plan to compare some attributes, and at the same time, if this attribute is null, what will happen? Normally in database systems, we use this null to represent some special cases for the attributes, and its physical meaning depending on the context. We have two common cases. We can use this null to denote some missing values. For example, if we know that Joe's bar has some address, but we don't know what it is missing, then we can set this address to be null. Sometimes some attributes can be inapplicable. For example, the value of the attribute spouse for an unmarried person will be null because it is not applicable for a person. Here let's think, if in the where clause and for the attributes we are comparing, we know them to be null, what will happen? If we have some attributes to be null, and we will define some Boolean conditions based on this attribute, then we can assign its truth value to be unknown. We are comparing any value which is a null actually, the truth value for its expression, for its condition will be unknown. Therefore, for the logic of the condition in SQL will be 3 values. Besides true, false, we also have this unknown as well. This is something we need to pay attention to when we are designing these conditions. So normally a query will produce a tuple in the answer if its value for the condition for the where clause is true. Right? We will do a select from where clause, and we plan to find some matching cases for our condition. Only the condition can hold, can be true, then this tuple will be valid. Otherwise, they will be illegal, right? They will be pruned. And these tuples will be generated or produced only if this condition is true. Therefore, when we have some null values for some tuples, if we have unknown as its truth value, and they will never be generated or produced in the select from where clause. I hope you can follow me, right? So for the conditions, we can have 3 different values, either true, false, and unknown. However, in the real world, we may define or design some very complex conditions. If so, how can we decide the values for the conditions? We provide you with a very simple equation we can use to decide the values, the truth values for a condition. Let's assume if we have a very complex expression for the condition, which is Boolean condition, right? And we want to decide if the condition is true or false or unknown for some data tuples. So a simple way to understand how is and or not work in a 3-valued logic, we can think of its true as 1 value, false as 0 value, unknown as 1/2 value. We can also think this and as the min function or as a max function, not as a function like a 1 minus some inputs. And if we have some complex conditions which is connected by this and, or, and not with some like true values, if we have an expression like this, we have true and inside it we have false or not unknown. Then the question is, what is it returning truth value? It will be very hard for you to answer this question, right? However, if we translate this expression into a function we showed above, we can get this value very easily. According to the previous example, we can set this unknown to be 1/2, right? We have not unknown, not function is not x equals to 1 minus x. Therefore, it's not unknown equals to what? Equals to 1 minus 1/2. Here we have this all false and this not unknown, right? According to the above function, we have all equals to max. Therefore, this false or not unknown equals to what? Equals to max. Inside it, we have not unknown equals to 1 minus 1/2, right? According to the previous example, we have false equals to 0. Therefore, this statement, this expression will be equal to max 0, 1 minus 1/2. And outside it, we have this and, this operator, right? We define this and as a min function as well. So we have min true equals to 1. Therefore, we have min 1 as well inside it, we have this expression. So we can translate this Boolean expression into a elementary algebra expression. Min 1 max 0, 1 minus 1/2. If we want to decide the truth value for this expression, we can just need to calculate the value for this elementary algebra expression in a very simple way. It equals to what? It equals to 1/2. Therefore, the truth value of this expression equals to 1/2. We know 1/2 is unknown. Therefore, we can say this Boolean expression, the result or the return value is unknown. Right? And it provides you with a very simple tool to help you decide the truth values for some complex expressions. We can translate this expression into some elementary algebra expression first, by using the rule that's shown here, and we can calculate the value for this elementary expression, and we can translate this return result back, denoting the truth value for the Boolean expression. I hope you can follow me right. So this is the three-value logic. We can calculate the truth value for the conditions, which are in a very complex way.